Okay, well, thank you for the honor of being the last one in here. I should also say thank you for an absolutely marvelous time in Cambridge the last couple of weeks. Certainly learned a lot of things. So it seems that over the last few months, the program has been doing a lot of work on the mathematical applications and the development of the theories of migration, things like that. And today I'm going to simplify everything to the point where we just have a few rules and we're going to be just tracking melts as these rules are going to change. So it's going to be at the level of mathematics that you're going to find absolutely ridiculous, as in low ridiculous, not high ridiculous. But the idea is that hopefully with these rule-based models of melt propagation, we can actually start to test some of the hypotheses about what's really going on and compare very simple predictions to actual observations. And that's some work that I've been doing for a very long time with a bunch of people. The one I mentioned, of course, Laura Hebert was a postdoc with me. Students Hailong Bai, Kevin Miller, who is now in Stanford. Wen Lu, who came, I think, to the second workshop. We've been working on some of those stories together, and I'll show you the results. Mark Ben, with whom I started this stories a while back. Trish Gregg was a student who was at the time, and Glenn has been helping us with experiments. Now, very often, oh, that was not good, right? Wonderful.
It's from some distance.
That's her.
That's
rules.
that's me. That's my computer. Don't worry about it. That's maybe. I hope it's not related to the fact that I'm having some computation in the background.
Oh, yeah, aspects running in the background.
Yeah, but it might be related to the fact that everything just froze.
The mouse is on this monitor at the moment.
Yeah, the mouse is on this monitor.
That might help.
Go to the last probe.
Yeah, I got it. Thank you. Okay, second attempt. Okay, well, all right, so I often give this type of presentation to a very broad audience, so I'd like to justify a little bit the study of mid-ocean ridges, maybe less relevant in here, but certainly this is coming from a textbook picture of the ridges, and this is the place where actually the largest output of volcanism on Earth is taking place. 80% or 70%, depending on the estimates of magmatic activity, happens on ridges, so it's not something to ignore. Of course, this is where you have formation of lithosphere plates, so very central to plate tectonics, and also supporting through the medium of hydrothermal circulation intense and vivid communities of extremophiles. So certainly a component of the Earth system that is key for the Earth as well as biology on Earth. And the whole system here, the thermoregulation, etc., is driven by the magma processes. So it's very important to know and understand what controls where the magma is located, where it's going, etc. At large scale, and I know you've seen some pictures like this before, the idea is that you have upwelling of the mantle that driven by the divergence between two plates along the at the ridge axis. And so as a result, you have a broad region over which melting is at least possible and has been detected by some geophysical means to some degree. There's a bit of disagreement about really how broad regions are, what are that shape, but we know that melt is being formed over several tens to potentially hundreds of kilometers away from the axis. And yet, when we get to the surface expression where the volcanism takes place, everything happens within a couple kilometers of the axis. So there's an intense amount of focusing that is taking place. Then the big question is, how do we explain this focusing? There's been a lot of model proposed. I understand you've heard some discussions about that, especially, I guess, Garrett's talk last week mentions a lot of these. Potential feedback with buoyant upwelling, pressure that was developed by McKinsey and Spearman and McKinsey several years ago, ideas about coalescing channels, anisotropic permeability due to foliation or shear bands, stories like that. What I will be focusing on really is the formation of a permeability barrier that actually prevents melt from going to the top of the Earth and instead has to kind of follow some barrier towards the ridge axis. Recently, barriers have been proposed to be controlled by grain size. The older story is that crystallization of the melt controls where those barriers are, and that's the one that I'm going to focus on more. Now, these are just schematic diagrams, and honestly, the level of my models is not much beyond the schematics. But the idea is to try to test these in a three-dimensional settings against observation, especially of variations of crystal thickness along the ridge axis. And these crystal thickness variations are going to be related to the segmentations of the ridge axis. So very often, mid-ocean ridges are seen as those lines, but we know they're broken by those transforms or by some other features. And so we're going to use the fact that you may have, in some cases, systematic relations between crustal thickness and the segmentation of the ridges as essentially tests for at least a very simple melt focusing process that I like to focus on. The approach is to integrate studies at many scales to build up the rule-based melt migration stories that I present. It starts, we do, for example, some work at microscopic scale on microtomography of some basalt and rock aggregates, like what we see in one of those reconstructions, where we can image the melt network inside a synthetic rock, and we can make some calculations out of that to figure out what's the effective properties of the aggregate. We put this looking at kind of a field constraints based on a little bit of exposures of ultralights and things. This was from Josephine Plato-types that tell us about channeling and some features of the melt extraction. And then really the work that I want to focus on today is how we take the lessons from those scales and implement it on a very large scale model of a region of the world. There is here a ridge, a transform, and another ridge. And we can try to make some calculations about how much melt is going where. Then we can then compare to, for example, the bathymetry of the ridge or the crustal thickness and stuff like that. So our approach is to take lessons from one scale and then apply them to a larger scale. Other people have been doing some coupled model, and I know you've heard a lot about them, using phase flow equations, McKenzie, or actually Berkovich and others, adding thermodynamics, Grenz's evolution, surface energy, etc. We can get some insight in terms of the coupled system, but essentially what I'm working on is to take this and simplify it until we get essentially these rule-based ideas. Let me skip this. And here I'm going to just give you the three basic rules already that are essentially at the basis of my melt extraction model. I'm going to give them schematically out of here. This is a cross-section through a ridge. The surface is up there, you have the ridge axis in here, and this brownish thing is the lithosphere as it thickens, as it cools and thickens off axis. Mantle follows the green lines up and then turns the corner. And there's a faint triangle there, which is kind of the classical region where most of the melting is taking place of. And you find in some textbook people who are going to tell you this is where the melt is located. In fact, based on those couple models I mentioned, we think that the melt is probably more located in a pattern that looks like this. And to explain this pattern, we can actually capture the melt transports that corresponds to this type of distribution of melt in terms of three different rules. There's the three acts that made up my title, the very simple stories. The first one is at depth in the region of where melting is taking place, often a little bit above it. Melt is mostly going to move upward vertically at a fairly high rate. So that's rule number one, step number one. I'm going to justify it more at length, but this number one is just melt is produced and just go up. It doesn't care about anything else, just go up. Number two, it's going to hit the base of the lithosphere and make a barrier where there may be a permeability barrier, accumulate in some kind of decompaction channel. I made it more discontinuous in here, but that's not actually going to be included in the details of the model. And the melt is going to travel along the base of the lithosphere due again to gravity, so it tries to go upward. It has to follow the slope. And so, for example, that's going to move it towards the ridge axis. And then there's a third step that we find is necessary. It's just to say, at some point, you have to break through that lithospheric lid. And we are going to be using actually observations about where you have tectonic damage in particular to say, okay, extraction is possible in here. So those are the three steps that I'm going to justify to you over the rest of the talk. Not justify them in terms of essentially basic physics about what might be going on, but also what type of observations they can explain, and for what observations it's actually necessary to involve one step or the other. So let's start with step number one. It always makes sense to start with number one. That is mostly justified coming from quantitative estimates of permeability and all of those stories. So this is the work that we've been doing with Wendy Tu and Kevin Miller and a few others. Essentially what we've done is in Glenn Gattani's lab, we've produced some aggregates of solid olivine plus or minus pyroxene, and mixed with some basalts, we put them at high pressure and temperature so that we have equilibration of the microstructure of those assemblages. And then we take the rocks, let it cool down, and move it to Argonne National Lab, where we zap it with X-ray cyclotron to make a series of images of the sample, which then get reconstructed into a three-dimensional microtomographic image. So this looks like a picture, but in fact, it is a 3D volumetric data set. We can see here, as we are looking into it, we can have an idea about where the melt is located in the interior of the sample. Those are cracks that come later on. We see olivine, we see pyroxene, and the melt is the darker phase. And this is just an idea of a sub-volume where we may be able to look at and try to better understand, because looking at the full sample is a little bit overwhelming. So we often just look at a small or a few small parts of the sample to get a better idea about how the melt is distributed. So here are 4 reconstructions of the melt distribution in some pretty small cube. Those are evidently not statistically significant, but it's just easier to see. For fairly low melt fractions of 2% until 20% melt fractions. And we can see how the melt is distributed. And essentially, even for those very low melt fractions, you have a very well-connected network of melt, in this case in tubules. As you increase the melt content, you're getting more and more films that are developing along the grain faces, not just in the junction between the grains. But essentially, even at small melt fraction, the smallest we were able to resolve, we have a very well connected network of melt. Then what Kevin did is to take a network like this, essentially just simulate the flow of the melt through that network so you get an idea about the overall permeability of this assemblage. And you can see here a visualization of one of those samples, and you have liquid going through, and you can see its trajectory. Of course, all of this is done numerically using Aviso, which is our visualization software. They have this capacity built in, and we are able then to figure out the relation between the melt flux and the pressure gradient we have to put across the sample, and from that we can evidently back out the permeability of that particular region of the sample.
I ask, what do you do at the bottom and top?
So they have this weird accommodation zone, which is essentially like a funnel. And so you just have to impose the pressure on that open tube of the funnel, and then the streamlines you can see spread out to enter wherever they actually can enter. Okay, it's in between the grayish zone, it's solid, so you cannot flow through. But yeah, so you impose a pressure here, you impose another pressure up there, and then you calculate the flux.
So you're imposing the pressure somewhere slightly outside
That's right.
the sample, so your permeability is somewhat affected by the...
It should be somewhat affected, but this is totally open, so overall the resistive part, is going to be in here. And I think there's some correction for the theoretical equivalent permeability of that thing. It's just a way to kind of equalize the pressure across there in a more dynamic sense. We also have a home rule, very basic code, which doesn't do that, but imposes the actual same pressure all over that there, which is not right either, and we'll get the same results. Yeah, it should go without saying too, don't hesitate to interrupt whenever there's a question. So anyway, we do this for a bunch of samples, and we have this relation eventually between the measured permeability and the permeability, sorry, what did I say? The measured permeability and the melt fraction or porosity of each one of those samples. And we can see a very nice parallel relations. That's some type of things that were expected theoretically. Theoretically, there's some models that give you n equals 2, n being the exponents of the porosity here. N equals 2, n equals 3 have been justified theoretically. And we got 2.6, which is kind of a nice thing in between some of those highly idealized system. But what's good about it is that we not only have that value, we also have the scaling parameters here. And these are really based on melt rock aggregates, not on analog materials or on. So this is, I would argue, the most reliable permeability estimates of the mantle for a given melt fraction. caveat, there's no fabric to this. This was completely isostatic, etc. But still, it's a pretty good number to do. And one of the things about it is you can easily calculate, based on the density contrast between melt and solid, how fast a melt would be moving in a network of a given porosity. Geophysical observations, except for one recent paper, would always tell you have only 1 or 2% melt at most underneath the major axis at any given place, which they have a very efficient extraction system. With these values, you would get meter per year of velocity of the melt through a porous network of 1% or 2%. That's much faster than that's quite a bit faster than some of the earlier estimates. But we think it's a little bit more reliable estimate, but also the good thing is that 1 meter per second is the type of range for which you can start to have some hope of preserving uranium series disequilibrium from great depth. So in fact, some of the ideas about how melt cannot extract fast enough to preserve some of this equilibrium is maybe not completely, it may not be such a problem after all. And that is using a 2% melt. If you have channelization, like for example, the cover of this program, you would have even faster, and in fact, 100 meters per year would be totally possible with a 1% average melt fraction. Yes?
So I just asked for that previous graph. It's the average grain size from each of your samples, that's the D, is that right?
Yes, that's right.
And so it's the standard deviation of that gives you the error bar and the permeability measurement?
Oh, no. Well, so the error bars that we see here, so again, the melt fraction is actually reconstructed inside of each sample. That's a model in itself, it's a tomographic model. So there has to be some uncertainty to how much melt is actually present in each one of our small volume. And that's probably a bit of an overestimate of the error bar, but it's based on just saying this is our standard, our preferred reconstruction of melt volume, just expanding 1 pixel or shrink it 1 pixel. Okay. And that gives us these error bars. There is no error bar on the permeability because it's a perfect calculation. But of course, there would be some correlation between, but we just haven't done that. It wasn't worth it. But yes, that means that when I tell you 2.6, you want to think 2.6 plus or minus, I think 0.3 is what we quote in the paper, and there's a related uncertainty on the parameters down there. I just didn't report that here.
Do you see much anisotropy in the permeability?
No. We actually, I don't have that slide, but we have been able to calculate the permeability anisotropy in this case. So, you put and there's some computation, not the one that I visualized. It's possible to say, okay, I'm putting the pressure gradient in one direction, but I can look at the flux outside. So you can have the full permeability tensor essentially within, I think, 1 per 1,000, it's isotropic. There's very little of diagonal terms, and the diagonal terms are within a per mil error of one another. So it's very isotropic. Right? So, all right, so U series used to be a big problem, but especially if it's not necessary, but especially if you take some kind of, concentration, you go so much faster in the channels that you have no problem preserving deep disequilibria in this process. So that's not again. Yes, again. Apologize about that. What I'm gonna do this. I'm afraid this might do it often. I will admit I've been having some problems with this computer last few days. No, that's not here. We were here. Okay, so that was for step 1. Now let's talk about the formation of this permeability barrier and what type of observations that it enabled us to explain. So the first hints of permeability barrier were actually proposed by Sparks and Parmentier in 1991, where they basically talked about, again, just a vertical migration of the melt, and if it gets to the thermal boundary layer, it's going to crystallize. At some point, those crystals can clog that pore space that I visualized earlier and render it essentially impermeable. So the question is, where does that actually occur in the Earth? For this impermeable barrier to form, you need a high crystallization rate. So with my postdoc, Laura Hebert, what we've done is to actually calculate the crystallization rate based on a thermodynamic calculator, MELT, calculate what would be the crystallization rate as the melt goes up, find out where it's very large to some level, and that enables us to kind of parameterize the temperature at which a permeability barrier would be formed, and essentially is 1240 plus a gradient of depth. So we have these thermodynamics-based justifications to where a barrier, if it forms, is most likely to develop. And then the idea is that as melt keeps on rising underneath it, it's going to accumulate in a decompaction channel. There is some evidence, geophysical evidence, of those decompaction channels happening in a variety of environments. Nick Schmer, a couple years ago, a few years ago now, published a diagram which summarizes essentially a bunch of locations where melt has been proposed to exist at the base of the lithosphere, so around that thermal gradient, which is also what we are planning for in the ridge environment. So, for example, of Japan, where you have the Pacific plate subducting, you can actually see, from receiver functions, regions which have a low velocity, potentially melt accumulated, and it looks like it's just been carried with the plate as it has been subducted. That would be this region here we see there. In the Pacific as a whole, Nick used some underside reflection of the lithosphere to try to find out where you would have this decompaction channel, and he found them especially close to where you have hotspots, so where melt is possible. And in the ridges, actually, this is where we have one of the worst constraints on the potential for melt accumulating at the base of lithosphere, just because of the depth where it happens. But for example, some 3D seismic reflections that were published a few years ago now show very close to the axis some regions where are potentially interconnected seals. And this would be the ridge axis in these 3D views. We're going off axis like that, and you can see essentially it's inside the crust, unfortunately, where you may have melt accumulation has slightly further off axis for the depth and the potential interconnection of the melt. So anyway, there are some views that you actually have a more or less thermally controlled region where melt can accumulate, and it kind of cascades upward towards the ridge axis. This is very small, only a few kilometers from the axis, and essentially the idea is similar type of process may be happening over the ridge system as a whole. It also should be said that some of those melt accumulation layers also have been suspected based on some ophiolite observations. So what can we explain with this? This barrier is going to be important in terms of explaining some of the melt focusing, as well as variations in morphologies between various types of ridges. So I'm going to give you a quick overview about some of the morphology and aspects of mid-ocean ridges. And the first thing, of course, is that ridges are often classified depending on their spreading rate at fast, so ultra slow, as we'll see. Here's a view of the fast East Pacific rise, which goes here and then turns transform, etc. Few things, of course, on it is those transform faults I already mentioned. We have a little bit of off-axis volcanism over a few tens of kilometers, which also tell us that's an indirect evidence that there is melt over a fair distance away from the ridge axis in this environment, including those seamounts. You have offsets and these things that are called overlappers that we'll be using in some respect. And the transform themselves, we know there's melt underneath it because in some cases there are some small intra-transform spreading centers, and they have zero-age lava in many places along the transform. So essentially, this transform in particular is kind of leaking melt at present. So we know there's melt pretty much everywhere underneath the seafloor in this picture. But of course, most of it ends up at the ridge axis. And using the concept of permeability barriers helps us explain the systematics of focusing in this environment.
And similarly, the seamounts are currently active.
That's right. In fact, the same crews that did the 3D experiments, they went over one of those seamounts and they found an active magma chamber underneath it. So yes, those are, they are pretty close to a zero-age crust, so they really cannot be old. They can only be younger than the crust on which they sit. When we go to a slow spreading center, you have a very different morphology. I'm following the ridge axis, and there's some big transform. It also has a very well-developed transform. The rift, instead of being a ridge, is now having a rift valley along the axis. Long-lived offsets, like here, the transform. we don't see any evidence of off-axis magnetism in here, which kind of tells us that the system is a bit more restricted. And there are those thin core complexes, which I'm not going to discuss at length today. So those are some of the morphological differences between fast and slow. About 15 years ago, there's been the recognition that there's a third type of major morphology, which are the ultra-slow spreading centers. They only happen in a few places, but they're going to be key for what I'm going to talk about. So in case you haven't heard of ultra-slow spreading centers, I'm going to just give you a quick overview about what they are. Here's an example of the Southwest Indian Ridge, and we're looking at about 300 kilometers of field of view here. The ridge axis is going on here, and some of the things you can see on it is that it's actually a very deep valley going down to 5,000 meters below sea level in cases, which is some of the deepest axis on the Earth. And key in particular, there's no transform offsets. We lost the potential of having transform in this environment. In many places, people have dredged the mantle directly on the seafloor, so there's a large swath of this that essentially has no crust, no oceanic crust on top of the ridge, which is very surprising. But when there is volcanism, it can make a very large seamount, which is right on the axis. Again, something that we don't often see in other environments. The other thing, and that's going to be the key really, is even though there is no transform, that ridge, as you can see, kind of has a swing to it, even on that picture, and they are what we call oblique variations in the obliquity of the ridge axis, which I'm going to go into a little bit more detail in a minute. And the patterns of whether you have transforms or obliquity is essentially going to perturb the melting system and produce some crystal thickness variation that we can explain with the concept of permeability barriers. Those ultra-slow spreading centers are found in the world wherever you have, wherever I put one of those stars. And the circles are where you have a slow environment. No, sorry. The reds are the ultra-slow spreading centers, and in many of cases, you have a star image that the ridge is actually oblique at that point. What does that mean oblique? I mean, the standard way is that if you have the ridge is going to open like this, orthogonal to the ridge axis opening like this. In an oblique segment, the ridge axis is at an angle, and so you're opening that way. And that turns out to make a lot of difference in terms of the melting system. So here's a view of the northern mid-Atlantic ridge, which probably we're not too used to see. It's on its side. Here's Iceland, Greenland, the North Pole. We're here. And so you can see the ridge, the mid-Atlantic ridge, north of Iceland, is actually having a lot of those swings, and there's not a lot of transforms. There's one here, there may be one here, but otherwise you have fairly continuous ridge axis, but you can see how it changes orientation all the time. These are obliquity variations. I did the projection so that the two plates are essentially always opening up and down in this diagram. So everywhere the ridge is not horizontal on the board, that means that you have some obliquity, like you can see in here or there. You have about 40-degree obliquity in those cases. And a lot of places where you have high obliquity, you will have what we call a ultra-slow morphology. So a lot of the ultra-slow spreading center are related to places where the ridge is also oblique. A place where we can really see the relation between morphology and obliquity is in the Southwest Indian Ridge at 54, 57 east. The opening is up and down on this diagram, and you can see the ridge axis is having orthogonal, oblique, orthogonal, oblique, orthogonal, oblique type of, this little sequence. And it's very clear from the bathymetry as well as crustal thickness variation that comes and magnetic anomalies, whatever. What you can see very clearly is much thicker crust where the ridge is actually orthogonal, much less crust when the ridge is oblique, etc. So you have this relation between ultra-slow spreading morphology and segments of the ridge which are more oblique than the rest. And so this is one of the observations we want to explain with the concepts of a permeability barrier. Another observations that we find in the Southwest Indian Ridge again, but a bit more to the east, 916 east, is actually the way that melt seems to be focused when the obliquity suddenly changes. So here, this is a very long segment of the ridge, often called a super segment, whatever. And what you see is that on the eastern part, it's actually pretty oblique. Here compares the ridge normal direction in black and the opening direction between the divergence between the plate in red. You can see that in this case, on the east, the ridge is almost orthogonal, so normal type of mid-ocean ridge. On the west, you have this highly oblique segment in there. And the fact that the red dots vanish tells you that the samples that get recovered from the seafloor have less and less crustal type of composition. Crust would be, the salt would be put as the red dots. We hardly see any in that region here, so we are clearly ultra slow in that place. And interestingly, there are these two seamounts, Joseph Mace seamounts in formal name, as well as the narrow gauge cross-axis high here, where essentially a lot of magma is being focused in this environment. And so using the idea of the permeability barrier and the way that it could affect melt trajectory, we can explain why the seamounts are actually in those particular places, as I'll show you in a minute. So the first thing I said is you have to have a relation between obliquity and spreading rate to explain those ultra-slow morphologies. And that may be related to the permeability barrier. Here I'm showing in this diagram a definition of what we might call the effective spreading rate. This is a view of the ridge axis, and the two dots here tell you the divergence of the plate. So you have an obliquity between the plate divergence and the normal to the ridge axis. It means that the velocity, the opening motion between the two plates, can be resolved in a ridge parallel and a ridge perpendicular direction. The effective spreading rate is essentially just a component of the plate divergence that's perpendicular to the ridge axis. So it's reduced compared to the main one, and the more oblique you are, the more intense the reduction here, as you can see from that really advanced equation. Anyway, it turns out, if you're making simple color flow models of what happens at depth, that this is the only parameter that controls the upwelling. The upwelling, the rate at which upwelling is occurring underneath the ridge axis is actually not proportional to the divergence of the plate, but to this effective spreading rate. Usually people just look at a 2D model, so they are the same. But if you want to look in this case, you have to, the upwelling underneath the ridge axis is proportional to the effective spreading rate. And therefore, the amount of cooling, so at depth there's going to be a competition between cooling from the surface and the upwelling, so you have essentially an equilibrium thickness of the lithosphere right underneath the axis. We calculated that equilibrium thickness for, as a function of the effect, how does it go? We calculated this equilibrium thickness function of the effective spreading rate in a few years ago with Mark Van. And what we saw here, so here we report, okay, we just use obliquity here to kind of spread out the observations, but we report the effective spreading rate for ridges that have been classified as ultra slow and ridges that have been classified as slow. And you can see that essentially no matter what the obliquity, etc., there is a critical effective spreading rate for which you have a certain, for which you have this ultra slow spreading morphology. That basically tells you that you have an ultra slow morphology if the thickness of the lithosphere underneath the axis is somewhere like 25 or 30 kilometer depth. That would be the depth of this permeability barrier. It essentially tells you that you have become this ultra slow spreading center if your barrier is so deep that the melt starts to really have problem to cross the lithosphere gets too thick. Okay? It's not related to a melt generation, it's really a melt extraction point of view, because unless you go to this one case, you would expect melt to be produced underneath the ridge axis, but it looks like in all of those cases, you have so much thickness, the barrier is so deep that the melt starts to have problem to get to the surface. Now, going back to that Southwest Indian Ridge, the melt has problem to get to the surface in this slow spreading center, but it does not have a problem to make it to those two seamounts there. So why are those seamounts located there? It's possible actually to look not just at the depth of the barrier, but also how it changes, especially in that region, to explain the focusing of the melt towards these axes. I like to always show a bit of the constraint. This is the bathymetry with, again, color-coded the type of rocks that have been recovered from the seafloor. We have a view, so we define that region 3 oblique segments, so it's 1, 2, and 3. They differ in the degree of obliquity. 2 is highly oblique, 1 and 3 are much less so. And they are separated by those seamounts, which, okay, Joseph Main actually is here, sorry for the arrow pointing wrong, and Narrowgate is in that place. It's just the same words that I said before, I just want to remind you. We have gravity anomalies from the region from which people have been able to infer residual mantle bouquet as well as crustal thickness, and we can see that essentially they are much thicker crust underneath the seamounts than they are elsewhere. And the zero level is a little bit, these are all relative thickness differences. And so the question is, can we actually explain the focusing and the thick crust underneath those two locations there? Turns out by using permeability barrier in 3 dimensions, that's actually something we can do. Even when just out of those observations, some diagrams like this one were written in which people were saying, well, you know, the lithosphere, whatever it's been defined, is going to be thinner where you have less of an obliquity based on the scaling that I mentioned earlier about the effective spreading rate, effective operating rate. And so melt that would be traveling along the base of the lithosphere should be focused towards those locations where you have, where you are between, where you are between the oblique segments. I forgot to mention, yes, there are those 3 oblique segments, but in between there was proposed that there would be a short orthogonal segment here as well as there, kind of in the offsetting those oblique segments. So there would be a little bit faster operating rate here, a bit thinner lithosphere right underneath those guys there. That's part of the story. But that was certainly a part of the story that was present in those type of cartoons that was published in a way. So we tried to be a little bit more quantitative about this. So we built up a regional finite element model of the location here. It's done with Compson multiphysics, and what we are using is essentially just a simplification of the ridge axis, and we have several visualizations of it. And this one you can recognize the long oblique OS2 segment, OS3 in 2 parts, OS1 in 2 parts, OS3 there, and those short intervening orthogonal segments where we hope eventually you're going to have Joseph maze and narrow gate. This, you know, it's we have a model which has temperature and stress-dependent viscosity. We impose just the divergence of the plate, mantle rises, equilibrate thermally, and out of that thermal structure, we can back out what's the shape actually of that permeability barrier according to the parameterization I described earlier. What you can see is, so this is just that surface, contour of that surface. The green thing, the green curtain is a projection of the ridge axis at depth. You can see that clearly the barrier is shallower right underneath the ridge axis, but it has a lot of 3-dimensional complexity to it. And so now the idea is that the melt that is generated anywhere in this model is going to rise, hit that barrier, and then start to travel along the barrier, along the direction of maximum slope, because that's probably the most efficient way to go. And so when you have a non-trivial shape, what the trajectory of that melt is also non-trivial. But we can solve for it. I now done apologizing about this, and I expect it will happen again. Sorry about that. So now I have to figure out where I was. Fortunately, I have a lot of hidden slides, so it's sometimes difficult. So here is the same thing, but seen from the top with the ridge axis in yellow. And those colors here just show the depth of the barrier. And the red lines would be the trajectory you would take if you go upslope along that barrier. So you can see that these lines generally go towards the axis, but there's a little bit of complexity to them. Like, for example, this one in here almost makes it to the ridge axis, but then turns around the corner. So the shape of the barrier already kind of perturbs the melt migration, and we'll try to focus it towards different regions. And if you remember the cartoon diagram that was step 2 about the melt going along the barrier, just in 3 dimensions, that trajectory is not always along the axis. It can have a component which is focusing in various places. But to really explain what we see in a place like Joseph Maze, which will be here in narrow gates, we needed to add that third step, that is to say, at some point, you have to be able to cross the lithosphere, and we're just going to tie that to the tectonic activity, maybe by some faulting or some damage that is going through the lithosphere. So the lithosphere is not intact where we actually observe there is a spreading center. This complex diagram, which I don't have time to get in detail, unfortunately, essentially just say that you're going to follow melt trajectory until either the slope is so shallow that you don't have driving force anymore, or you enter this damaged region and now you can make it to the surface. And based on this, we can actually explain the presence of Joseph Maze as well as narrow gates. Here, this is a diagram of the expected crustal thickness from our model as we are moving, walking along the ridge axis. There was a big transform, we didn't talk about it. The first oblique segment where Joseph Maze is, the long oblique supersegment, narrow gate, and then the less oblique segments on the east part of the model. You can see that in both cases we have those anomalies of a few kilometers extra thickness of crust just at the location of those seamounts, which corresponds to the observations. Don't get fooled, there was a lot of models where it didn't work, but this one did. But very interestingly also, the origin of those two seamounts are different. For Joseph Mays, what we have essentially is, it's a little bit of a orthogonal spreading surrounded by oblique ones, so the barrier actually is shallower right there. So the shape of the barrier, as we can kind of see on this diagram, essentially a bowl, a soup bowl that is inverted. And so all the melt follows that and just goes to the apex of it. It's just like, the smoke on the chimney, on the roof type of ideas. It just goes there because that's the apex of that bowl. And that's where the seamount said, okay, good. It turns out now again, that's not the case, because the obliquity is much less on the east side than on the west side, and therefore, yes, it tries to be, that bowl essentially is tilted. And so what you can imagine is that if it's tilted enough, which is the case there, you don't actually have an apex. You can follow it and you're going to keep on going. You can have your soup bowl, you put some water in it. If you tilt it, eventually the thing keeps on flowing. So if we only had step 1 going up and step 2 along the barrier, the melt would keep on going along the barrier until it ends up somewhere here, or it ends up in the central Indian Basin or wherever. Okay. The fact that it all gets focused here requires that you take that third step that say there is some tectonic damage in that particular location. All the melt that is produced around the oblique supersegment there essentially travels along the ridge axis, and when it has these little kinks, essentially is the first time that it is getting close enough to a ridge to actually be extracted. So the fact that Norgate has a lot of melt is not because a lot of melt is produced here, or it all goes over there. It's just that as it's traveling, this is the first time it hits a region where extraction is possible, and therefore all of that melt that was kind of pulled is just going to make it to the surface. So in a cartoon diagram of this process is you have this region, the barrier, you're focusing along it, and then this is the first time you encounter this crustal extraction zone. And you can then make it to the surface, and because you have pooled melts from various regions, you have enormously high crustal thickness in that location. I should also say that a lot of this melt is much lower degree melt than what you typically have in the ridges, so you expect some chemistry, some weird chemistry in that location, and in fact that's the case. I think it's enriched in high potassium, but I'm always confused about what they mean. But even before we produced this, Henry Dick and Jeff Sandwich were telling me, yeah, you need a lot more low-degree melt to explain the location of that seamount, the composition of the seamount, so that worked well. So we went through step 1, which is basically based on the microphysics of things, step 2, which is based on the thermodynamics of crystallization, and then step 3 seems to be required to explain at least some of those seamounts at ultra-slow spreading center. So that's the 3 steps that I've been talking about. Now, you may be saying, well, that was very nice, but you've only been looking really at those ultra-slow spreading center. That's true. We did that in part because as there's much less melt in that environment, we may be more sensitive to some of those small processes. When you go to a very fast spreading center, you flush with melt, so you may not be able to reconstruct those subtle variations in the melt trajectories. But it turns out, even at a very fast spreading center, there are some evidence of these processes that I'd like to describe to you in a minute. So let's go to now the specific rise. You have ridge transform ridge. This is the Sequeiros transform. It's pretty long. It's very well known, very well evaluated. And a few years ago, Trish Gregg figured out something which, actually, the first time we tried to publish the paper, we got rejected. People saying, that cannot be right. I said, well, sorry, it is right. The idea is that there was thicker crust along the transform than there was in the region surrounding it. The standard picture, which is known for like 30 years or more, I forget, comes from slow spreading center where you have ridge, transform ridge, and from the bathymetry, the gravity, this is the residual mantle Bouguer anomaly, you see that you would have high gravity anomaly, meaning thin crust along the transform, which makes sense. The mantle is hot here because it's upwelling. It hasn't had much time to cool. At the transform, it's cool from both sides. The mantle is cold, and so you don't have much melt, etc. Everything's nice and dandy. But once we did the same analysis for the fast spreading center, which surprisingly nobody had really looked at until then, we find instead a gravity low along a residual mantle of Gaussian anomaly low along the transform, which is interpreted as a thin crust. Doing this in a lot of places, we find that in fact, at an ultra slow spreading center, you would have a thin crust along the transform, and at fast one, you could have a thick crust along the transform. So a very surprising idea. Why do we actually have that thick crust? It turns out the simple three-rule process that I mentioned is totally able to explain not just the fact that you could have thick crust and transform and fast spreading center, but also why you have that difference between fast and slow spreading centers. So to do this, we did an even simpler model than before, just ridge transform ridge, so that we can kind of change the parameters at will and look at a continuum of solution. This work that was published last year by my student Haiyong Bai. And going very quickly, you look at, don't crash now. You look at the depth of the barrier, you look at the trajectories. And one of the things which is really key is to realize that as you're going up that barrier, when you're far from the transform, you just go to the ridge axis, everything's fine. But when you're close to the transform significantly turns those trajectory around until eventually some of the melt goes there, crosses the transform, if nothing else happened, would cross the transform and end up in the ridge axis about that location there. Okay? That's just based on the thermal structure that you expect underneath the transform. I'm going to skip that one, it doesn't matter much. And the thing is, actually, let me come back to this one if I can. The idea here, and how to explain the observation I just mentioned, is that in a slow spreading center, the melt is able to essentially go underneath the transform and avoid this this melt extraction zone. It's too deep, and therefore it keeps on going until it gets close to the surface, which only happens near the ridge axis here. Whereas in a very fast spreading center, instead, this melt, as it's trying to sneak underneath the transform, is already shallow enough that it can get extracted. So there's a depth to which you can have extraction, and essentially when you're fast, all this melt does not end up in the ridge, but end up in the transform itself, which adds to the crustal thickness of the transform. A rendition of the crustal thickness variation that we'll get from here, so this is how long integrated the crustal thickness over time. You have here the ridge axis, you have whatever variation of crustal thickness, that's mostly noise, and then nothing is going on. Close to the ridge transform intersection, at time 0, you have no crust there. Can be removed, but you have no crust. But as you go on over time, and that plane has been dragged, there's a continuous flux of melt that get added to the transform, to the point that eventually you have thicker crust in the end of the transforms that you did when you started at 0H. Here's a comparison of the crustal thickness mass it would get for slow slipping or fast slipping transform fault, and you can see here the region of thickened crust that is due to essentially melt not being able to make it to the ridge axis, but instead being accreted along the transform. This works well in the idea also that you have, as I mentioned earlier, 0H melts in there, so you have kind of always a bit of magma leaking through some of those transforms, especially Securus. And we can explain that based on essentially the depth of the permeability barrier compared to the melt extraction zone. Haiyong did a lot of models in which he systematically varied the depth of the melt extraction zone, how wide from the tectonic plate boundaries that melt extraction is possible. There's also a long strike redistribution that is kind of due to diking, crust holes type of processes, etc. So he made a whole variety of models and found that the observations in terms of crustal thickness difference between transform and surrounding ridges as a function of spreading rates, those observations can be explained by two groups of models, group 1 and group 2. The parameters is in group 1, you would have very long, if you can distribute the melt for very long distance at crustal level, extraction goes to 15 kilometers. Whereas in group 2, the extraction goes, you can extract melt even if it is like 30 or 40 kilometer depth, but you cannot redistribute it along axis very much. That's kind of a trade-off. But there is an additional test, is that this group 2, although it worked well, when you go to slow spreading, let's see, when it goes to slow spreading, the group 2 says that there should still be some leaking of some melt not a lot of it, but there should still be additional melt coming along the transform, and we don't see those 0H melts in the transform in slow spreading. So we favor group 1, which tells you that the barrier needs to be about 15 kilometer depth before the melt gets extracted, and then it can travel fairly long distance along the axis. So schematically, these are the relation at the fast spreading and the slow spreading ridge. It's vertical exaggeration, obviously, but you have the box there is where the melt would be possible to be extracted, and you see the cooling effect of the transform is present in both cases, but in the slow spreading rate, the barrier is deep enough that it doesn't enter that melt extraction zone. At fast spreading, it does, so the melt goes up and boom, enters the zone and makes it to the surface, which is a way to explain the observations that you have thick crust in the transform at fast spreading regions. So I'm going to stop here, leaving you with this beautiful diagram, super fancy diagram, but you can see that there were actually a lot that went behind actually constructed these 3 rules, which I just want to summarize. Number 1, the melt goes up mostly because of its buoyancy. It goes very fast. It's highly permeable, so you have very rapid vertical abstraction until you hit a barrier, which in our case is thermodynamically controlled, and you travel along it until you go to the surface at a predefined tectonically damaged zone. It explains a lot of observations, and I didn't have time to talk about other places, but we're looking at continental rifts, Mars, and subduction zones. I used to think about hotspots, but haven't recently, where we also see evidence of these same 3 processes being active. So, with this, thank you for your attention.
Thank you very much, Laurent. Questions?
I'm dozing in and out, sorry.
I didn't notice.
Still, even though, yeah, there is, Mark Spiegelman and what's Mark Postdock's name?
Ian Wilson.
Yeah, they made a big deal about the compaction pressure and sort of the effect at depth. Sort of countering these models from Manuel Facendo, who sort of done this. Just have the straight buoyancy, it goes straight up, hits the lithosphere, and moves over. And they try to say, there's a strong effect of a low pressure zone drawing melt off to the side. I mean, can you comment on that? Can you make an estimate of how much this would affect your model to actually have more of this compaction driven flow and the compaction pressure that drives?
Well, I
It
mean,
would affect your step 1.
yes, it would affect the step 1. I mean, here I make them go vertical and go on side. This is based on scaling by the velocity, but also the type of pressure differential compared to what you would get from it's mostly corner flow theory, which is a simple one I can calculate. Obviously, if you're going to put, and there used to be those trajectories that would kind of dive and turn around. I represented them in a more cartoonish manner. The thing is, you kind of look at what scale you have this, you have the pressure gradient from this compaction dominating, and it all kind of depend on compaction length, we don't have to put constraints on, right? But the estimates I was coming up with are, by that time you already had a ridge axis just a few kilometers away, so you needed a different process for the whole thing. I think what's going to be more of an effect on this are the kind of, so one observation that really doesn't work with this is the one that Kerki and the others have done about melt conductivity at the specific rise, where they have this blob, which is at this diagram, although there's no scale, but that it would be kind of like this, but it looks like it's sloping at much steeper angle than what you would expect from the thermally barrier. Actually, I think that was one of the slides that Garrett had, which I may have copied, but I'm not daring. And that gives me a lot more problem in terms of reconciling their observation with this model, but the idea is that you may have shear bands that would be producing anisotropic viscosity, or Andrew Turner's model of grain size, essentially producing a low permeability region there, which could potentially at least slow down, if not completely redirect the melt. Those are things to be looking at as well. So there's no doubt that this process is going to have to be a little bit complex, and that's why I like to just make a cartoon, but essentially those things could be turning over. That would not be a huge problem.
So you say you've changed the permeability value It's a lot
Mhm.
different to
Well, it's a
previously
little bit, yeah.
thought, and
Yeah.
that you now think you can get away with just having diffuse porous flow without the need for any kind of channelization.
Well, yeah.
Am I right? Is that
We-
am I understanding that correct? Or?
1 meter per year is very much the minimum that you want to go at. Okay, you want to go faster than that to really make sure you preserve this equilibrium.
Yeah. Sure.
So the channelization is still very helpful in terms of going meter per year, but you don't need like what was calculated before, 50% porosity or whatever. That's
But what were those previous things based on? So I mean, this is based on doing a scan of a rock and then doing a numerical
Yes.
calculation based on your
So
scan.
a lot of the early models were coming from essentially modeling what would be the equilibrium geometry of the melt. So it was based on the textural equilibrium. And that was probably a semi-identical model, like one of those constant curvature. But it also assumes a constant grain size. Okay,
Constant and uniform
because there's a lot of
grain size.
symmetry that is put into the system. Okay, you kind of say this is the type of shape of grains, and then you can calculate what is the shape of the melt rock, the melt grain interface, and that's all nice and good. And if you do that, that's where I think you have n equals. I forget if it's n equals 2 or 3. I'm always bad on that. But you find one of those relations, and you find the C equals 50 with different relations, and that turned out. In our case, with the heterogeneity, it makes sometimes a bigger channel than the average one. And this bigger channel, especially for permeability, is very efficient at getting the fluid through.
Okay, so it's because it's polydisperse. Is
That's
that-
right.
Am I using the right word there?
So
It's a different grain
if
size.
you look, yes, that's right. So the heterogeneity helps going faster through the sample at equal melt content. Okay, and let me try to find out that animation. You can see how most of the melt goes in that direction, right? Very little goes in here. So you don't have a homogeneous flow through those rocks, and so because of the fact that a big conduit can get it's the square of the radius or something like this, you can get much more flux through that, so it's more efficient than if you had a uniform grain size.
Do you have any further questions, Laurent? In which case, can we just thank Laurent once again? Thank you very much.
Thank you.